Hello. This video is for Chapter 1, Lesson 2 of the text that's provided on the class webpage. And you can find that on the class webpage on the tab that says Textbook. You can find that there. So this is titled Powers and Exponents. So we're going to learn what powers and exponents are. We see over here in our vocabulary that we have power, base, and exponents. Those are our three vocabulary words. And you can see right here, they're all on the first page already, right? So we're going to hit that vocabulary kind of early. And our objective is to use powers to describe repeated multiplication. So repeated multiplication is what powers are all about. So let's go ahead and start taking a look at it. So a power is the result of repeated multiplication of the same factor. For example, the number 125 is a power because 125 is equal to 5 times 5 times 5. Notice that all of these are the same factor. We talked about in the past that the numbers that are being multiplied are called factors. So whenever we're talking about factors, we're talking about numbers that are being multiplied times each other. So here we have 5 as the factor 3 times, and since it is the same factor, we can represent it using a power. So a power can be written in a form that has two parts to it. So one of those parts is a number called the base, and another number that's called the exponent. The exponent shows the number of times that the base is used as a factor. So this illustration that we have here, this demonstration here, we have 5 and a 3. Well, 5 is the base, and you'll see that it becomes the factors that are being multiplied times each other. And then 3 is the exponent. Well, notice that 5 is being multiplied times itself 3 times. So the base 5 is used as a factor 3 times. So looking at the vocabulary here, the number or the factor that's being multiplied times itself is known as the base. And then this number, we call that a superscript. It means like Superman flies up in the air. So whenever it's raised up to a level above the normal level that the 5 is, we call that superscript. If it were down low, and that's in other places in mathematics, we would call it a subscript. A submarine goes underwater, so sub means below. So subscript is down low and a superscript is up high. So the 3 is a superscript here. We call that the exponent. So together, the base and the exponent create what's known as a power. So for our vocabulary there, the key concept to understand is that we have a base, the factor that's being multiplied times itself, the exponent, which is the number of times that that factor is being multiplied times itself, and together a base plus an exponent create what is we call a power. All right, so moving along to the next page here, we have a table, and the table shows how to read and write powers. Numbers raised to the first power, such as 12 to the first, are usually written without an exponent. Any number that we have, we could raise it to the power of 1, but in the end it just equals itself, so there's really no need to list that power of 1 there. So we would have it as a power with a base and an exponent, 12 to the first. In words, we would say 12 to the first power. And then over here, the value of that, 12 to the first, would just simply equal itself of 12. The second one, 0.5 to the second power. We say 0.5 to the second power, or we could say 0.5 squared. Here we have 0.5 as a factor being multiplied times itself twice. The base is 0.5 twice because the exponent is 2, and whenever we do that, we get 0.25. Now, I have the little man here standing on a square, and that kind of relates to the second row here, where we have the idea of something being squared. And the reason for that is that a square, if we talk a little bit of geometry here, a square is a quadrilateral, and we find the area of quadrilaterals by taking the length times the width, and that'll give us the area of a square. Well, it happens to be that with a Square, by definition, a square is a quadrilateral with 4 congruent sides or equal sides and 4 congruent angles. That is to say that the angles right here are all congruent. In this case would be 90 degrees for that angle there. And so if we just say that one side has a value of A, then that means all the other sides also have a value of A. So we say that the formula for the area of a square is equal for area, and we'll use a capital A, is equal to the side lengths. And I guess I really should have gone ahead, I suppose, and used an S for side, right? So if we did the length times the width, we would have S times S, S times S, which we could also say is S squared. So that's why anytime anything is raised to the second power, we could also call that squared instead of to the second power. Here we have 4 to the third power. So 4 is the base, 3 is the exponent. Together they make a power. And we would read this as 4 to the third power, or we could call that 4 cubed. And that would be 4 times 4 times 4, the base times itself, the number of times equal to the exponent. And 4 times 4 is 16. 16 times 4 is 64. And that relates to this Rubik's Cube that I have down here. So with a Rubik's Cube, you have a side length here, a side length here, and here we actually have another dimension, the other side length. So we have length, and we have width, and we have height. So in geometry, if we want to know the volume of a cube, we would have its length times its width times its height. Well, a cube, by definition, has equal length, equal width, and equal height. So in this case, we would just say its volume is equal to the side length times the side length times side length, and we would have V equals S squared, or not squared, but S cubed. So this is why anytime that something is raised to the third power, we could say that it is that base number and cubed instead of to the third power. Either one is fine. Usually most people use the squared and the cubed concept. And then once we move past the power of 2 and the power of 3, then we just simply say whatever the base is raised to whatever the exponent is. So 8 to the 4th power. And we have 8 times 8 times 8 times 8. And on these here, if I were trying to do this without the book telling me that it's 4,096, I like to separate these and do 8 times 8 is 64, and 8 times 8 is 64. And then I would, if I were doing it by hand, not using a calculator, then I would go ahead and I would stack 64 times 64 in order to get whatever the answer was. And in the end, we would end up with, I suppose I could go ahead and do that, right? 4 times 4 is 16. Carry the 1. 4 times 6 is 24. Add 1 more, it's 25. And now I'm going to do the tens place here where the 6 is. So I'm going to put a place holding 0. And, well, 6 times 4 is 24. Carry the 2. And 6 times 6 is 36. Plus 2 more is 38. And now I want to add these together because here I have what came from the ones column, this 4, and here I have what came from the tens column, the 6. So I need to add those together. I have 6, 9, 8 plus 2 is 10, carry the 1, and I get 4, so 4,096. Another way I could have done that is through the lattice method. I could do 64 times 64. This one's kind of cool. And then I make this here. So I have a column for the 6, column for the 4, then the other 64, column there and a column there. And then I'm going to put little lines through like this, through diagonal. Now, 6 times 6 is 36. So I'm going to put the 10s there and the 1s there. And I should have made this a little bigger, I guess. 6 times 4 is 24. And 6 times 4, here this 6. Notice that this square here intersects 6 times 4 is 24. And 4 times 4 is 16. Now I'm going to start adding, going diagonally. So I'm going to go this way here, bring the 6. 4 plus 1 is 5, plus 4 is 9, and 2 plus 6 is 8, plus 2 is 10, carry the 1, 3 plus 1 is 4, and now 4096. So either way, both times I come up with 4096. So traditional algorithm over here and the lattice algorithm over here. And this will work for really large numbers. If you had something like 3,942 and you want to multiply it times 79,163, lattice method would work really well for that. So a little bit of bonus stuff there on multiplying numbers times each other without using a calculator. So on the next page here, example 1 says using exponents. And it says to write the product using exponent. Well, here we have a base of 13, and what shows up 4 times. So our base is 13, and our exponent is 4, and the base is 13 is used as a factor 4 times. Here we have 0.2 is the factor 3 times, so it's 0.2 to the third. Notice that we use parentheses to kind of hold that decimal number in there. That's pretty common there. And then on this one here, it looks like n shows up 6 times, right? N's the factor, it's the base, it's 6 times, so that is the exponent, and the base n is used as a factor 6 times. And then finally on D, we have t as a factor, it looks like 5 times, so it's t to the 5th, because the base t is used as a factor 5 times. Checkpoint here, write the product using an exponent. Well, I have 3 10s, so I would have 10 as the base. 3 is the exponent. Here I have 4.3 is the base, and it's twice, so I'm going to use the exponent there. Notice that if it's a decimal, it's usually held in the parentheses there. And then I have x as the base, and it shows up 4 times. It's a factor 4 times, so it's x to the 4th. The reason I put in the drum over here is that, well, this is a bass drum, right? So I often use the memory device with students, explaining that the drum is the bass, and like let's say 5, right? And how many times she's going to hit it is the exponent. So if she hit it 6 times, we'd say 5 to the 6th. So the bass is the drum that's being beat, and the exponent is the number of times that we're going to hit that drum there. Now that might be a tough one to figure out by hand. That one's kind of crazy there. These here, first 3 are 125, and then the other 3 are 125, and so we can multiply 125 by 125 to get that. And that one I don't have memorized, and I'm not going to take the time to punch it in the calculator and see. But little strategy there on dealing with exponents. I think it's a little easier than 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625, I believe. And 625 by 5, see where it starts to get a little more trying to do it in your head. That could be a little challenging. In the second example here, we have evaluating powers with variables. Well, we know that evaluate means to substitute and solve. So here we're going to evaluate the expression x to the 4th when x is equal to 0.5. So notice that x is in the position of the base. So we're going to substitute in that 0.5 for the base. And then whenever we stretch that out, we have the factor of 0.5 4 times. And whenever we multiply all that out, yep, see 5 times 5 times 5 times 5 is indeed 625. However, we have 1, 2, 3, 4 numbers behind the decimal, so we end up moving the decimal over 1. Well, better use a pen there. We move it over 1, 2, 3, 4 times. That's why they end up with this big decimal number here, because we have to move that decimal over. All about multiplying decimal numbers. So in the examples here, evaluate the expression when m is 3. So if we substitute 3 in for m and square it, well, that's equal to 3 times 3, and that equals 9. What about, let's do m to the 4th. So 3 to the 4th. And this is a good place where I was talking about that example of strategies of doing these by hand, right? So that's the base 3 4 times. I could do 3 times 3 is 9, and 9 times 3 is 27. And then I might have to think a little bit about 27 times 3 to get whatever the answer is, right? Sorry, looking at arrow there. There we go. But another way I could do it is I could know, oh, 3 times 3 is 9, and these two 3's multiplied times each other are 9. Bring down that multiplication sign. Oh, hey, I know what 9 times 9 is. 9 times 9 is 81. So 3 to the 4th would equal 81. This page here refers to the idea of squaring and cubes, right? It's based on geometry concepts of the area of a square or the volume of a cube. Kind of alluded to that and talked about that earlier in the previous page. So using formulas, a formula describes a relationship between quantities. Some formulas involve powers, such as the area of a square and volume of a cube. For example, you can use a formula to find the area of a square or the volume of a cube. Area is measured in square units, such as square feet or square centimeters, whereas volume is measured in cubic units, such as cubic inches or cubic meters. So we have an example here of a real-world problem using powers and formulas. We have ice sculpture. An artist uses a cube-shaped block of ice to make an ice sculpture for a competition. Find the volume of the block of ice. So we know that volume, from what we've seen on the previous page, is the length times the width times the height. And notice that the length, width, and height are all 20. So this is a cube. By definition, it would be a cube. Otherwise, we get into rectangular prisms and so forth. But we're not there yet, so we'll just deal with this cube. So use the formula for the volume of a cube. V equals S squared. Well, we're going to substitute in that 20 and square it, and we get 8,000. So the volume of this cube is 8,000. 8,000 what? 8,000 cubic inches. It's in inches, and since it's volume, it's cubic. So just like we had S cubed. Notice cubic, we use the word cube there, S cubed. So in the real world, ice sculpture, a cubic inch of ice weighs about 3/100ths of a pound. That would be 0.03. If the artist carves away about 2,000 cubic inches from the block in example 3, about how much does the resulting sculpture weigh? So we have to first start off with what we have at the beginning, the 8,000, and she's going to carve away about 2,000 of that 8,000 right there. So if we knew the difference, we'd be good to go. We know that difference is, from previous lessons, it is subtraction. So if I figure this up, I'd have to multiply. Each cubic inch is 0.03. So that's repeated addition. 0.03 plus 0.03, etc. Addition, not multiplication. So we could say 8,000 times 0.03. So that's going to be 0, 0, 0. I'm getting that from 3 times 0, 0, 3 times 0, 0, 3 times 0, 0, and 3 times 8 is 24. And we have 2 decimals here. We have 0 decimals here, 2 after the decimal, 2 number values, 2 places after the decimal. And 0 plus 2 is 2, so we're going to move that decimal over 1, 2 places. So right there we have this whole block is 240 pounds, right? LBS for pounds. Now she carved away 2,000 pounds, so we need to find out what 2,000 pounds is, because when she carves away, it's taking away from the original weight of 240 pounds. And we're going to multiply that by 0.3 or 0.03. Again, 0, 0, 0. And then 3 times 2 is 6. We have 0 decimal places, 2 decimal places. 0 plus 2 is 2. So I'll move that over 1, 2 places, and we end up with 60 pounds. So she took away, this is what she carved away. So she carves away 2,000 cubic inches. So 60 is what we're taking away from 240. So we get 240 minus 60, and 0 minus 0 is 0. We can't take 6 away from 4, so we're going to borrow from the 2 and throw that 10 over here. We're borrowing a 1, adding it to the 4. We're actually borrowing 100 and adding it to 40. But 14 minus 6 is, what is that, 8, right? Yep, and then I have the 1 to bring down. So all in all, the weight of the sculpture itself is about 180 pounds. And I think that brings us to the guided practice. Vocabulary check. Identify the base and the exponent in the expression 13 to the 5th. Well, the base is the factor that's being multiplied over and over, so the base is 13. And the 5 is the exponent. Together, the base and the exponent make what is known as a power. How are the expressions 3 to the 4th and 4 to the 3rd different? Well, 3 to the 4th means 3 times 3 times 3 times 3, and 4 to the 3rd is 4 times 4 times 4, right? The base is 3 4 times, and here the base is 4 3 times. Well, we know that this is 9. 3 times 3 is 9. 3 times 3 is 9. And together those make 81. And then 4 times 4 is 16. And then take that, multiply that times that 4 to get, let me see, 4 times, here's my mental math on this. 16 is 10 plus 6, right? So 4 times the 10 is 40. And 4 times the 6 is 24, and together those equal 64, right? So 64 is indeed our answer there. Another tricky mental math here I'll share with you real quick before we go on is I could rewrite this 4 times 2 times 2 times 4, because I just took this 4 here and split it into 2 times 2, right? Then I could do 4 times 2 is 8. And here, 4 times 2 is 8. And then now, 8 times 8 is 64. That would have been a lot easier than what I did up here in the first place. All right, skill check. Write the power in words as repeated multiplication, then evaluate the power. I'm not going to write these out in words. I would write this in words. I'd say 12 to the 2nd power, 12 squared. And then if I evaluated it, 12 squared, well, 12 times 12 is 144, which is gross. If you're wondering what I mean, 144, like if you bought 140, how about like bottle rockets? You ever go on 4th of July and bought bottle rockets? They come in a pack of 12 bottle rockets wrapped up into a larger pack of 12 packs of 12. And those are referred to, whenever you go buy them, you buy a gross of bottle rockets. So gross is a word that we use to describe the number 144. So that's why 12 squared is gross. Another one here, 1.2 cubed. We would write that as 1.2 cubed in words. This one here, 1.2 times 1.2 times 1.2. I'd have to first, let's see, 1.2 times 1.2 times 1.2. And it might be better to write that in parentheses. That dot starts to get mixed up with the decimal, right? Now, this one here, I might have to do 1.2 times 1.2. Well, I know that 12 times 12 is 144. I don't really need to use the algorithm. And here I have 1 decimal place and 1 decimal place, so that's 2 decimal places. So I move it over 2 places, I would get 1.44. Now, I have to multiply by the third 1.2. So I'd have to take that 1.44, and then I'd have to multiply it times the 1.2. Well, here's some good practice on multiplying decimals. Notice that the decimals are not lined up with each other like we would in addition or subtraction. I just kind of act like they're not there for now. And then I'm going to do 2 times 4 is 8. 2 times the other 4 is 8. 2 times 1 is 2. Now let's put a placeholding 0 and do the tens column. And 1 times 4 is 4. 1 times 4 is 4. 1 times 1 is 1. Now I need to add these together. And I would get 8, 12, carry the 1. 4 plus 2 is 6, plus 1 more is 7. And bring down that 1. And now I have 2 place values after the decimal here and 1 place value here. So 2 plus 1 is 3. Then you move the decimal over 1, 2, 3 places. Yeah, I know, a lot of crazy work, right? Probably be easier with the calculator there. So 1.728 would be the answer for number 3. Evaluate this expression whenever k equals 6. Let's see. Boy, this one's going to be kind of fun down here. Let's do 10. I guess we'll give 10 a try. So let's go ahead and substitute in 6, because we're substituting a k, to the 5th. This is going to equal 6 times 6 times 6 times 6 times 6. I might want to use a calculator for this one. Let me see. These two 6s is 36, and these two 6s are 36, and bring down the multiplication sign, and that there. I might want to multiply 36 times 36 and get some number here, and then multiply that number times 6 to get that answer there. However, if I use a calculator here, and I just put in 36 and hit the, oh, it's not squared, so let's clear that. It is 36 to the 5th power, and we end up with, wow, that is, oh, I put 36. Silly me. Hold on. I did, you can't see it there, I did 36 to the 5th power. So let's clear that, and let's just do 6 to the 5th power. And wow, it's still kind of a big number. It is 7,776. Yeah, I would have been doing some math for a while, wouldn't I? Calculator is a good way to know how to do this. There are buttons on it for those special things. As a matter of fact, let's go ahead, and I'm at 26 minutes now. I'm going to go ahead and pause this for a second. I'll pull up a calculator and show you how to use some of the buttons that are on a calculator you might be looking for to do some of these more complicated ones, like 6 to the 5th. The object of the lesson here is to understand what a power is, what a base is, what an exponent is. It's good to know all these algorithms to do the multiplication, some of the shortcuts to do it, but if you get something like 16 to the 7th power, probably wouldn't expect you to work that one out by hand. So I'll be right back. Hold on a second. All right, so I am back with my calculator, and this is kind of a fancy looking calculator. This is known as a graphing calculator. It is a computer version of the one that I have here on my desk. This is a TI-84. See, I'll put that there. That's a TI-84 plus C. The C is for color. It does things in color, a lot of cool stuff there. So, but at any rate, and once right now COVID's going on, but whenever we're actually in the class, I'll have these in class for you to use. So you might find buttons similar to this on your cell phone. If on your cell phone calculator, many cell phone calculators, if you use the phone, grab my phone here. If you have the calculator open and your phone is in a portrait view like this, up and down type long ways, and then you turn it sideways, a scientific calculator will come up instead. I'm sure many of you know that, but for those that don't, and the scientific calculator will have extra features and buttons on it that you won't find whenever you're in standard mode like this. So with that said, I'm going to go ahead and clear this out. Clear. So here's my button panel here and my screen over here. So let's consider this k to the 5th, and that was 6 to the 5th. So I could just do 6. Let's go back. Actually, I'm kind of getting ahead of myself. You can tell I really wasn't planning on doing the calculator part here. Let's say I want 6 squared. Well, there's a button over here that has x squared, you'll see right here. And so if I just hit 6, get that up there, and then I hit squared, and then I hit enter down here, it'll tell me it's 36. But what if I want something else, like 6 cubed, right? Well, there's not really a cube button, but we have this thing called a caret button. It looks like a up arrow, and you'll find it right here above the 4 operation buttons. Notice that these operation buttons are one color. The number pad buttons are another color, and the other buttons here, other functions, are different colors here. But these all do other things. But your main divide, multiply, subtract, and add are here, and then this red button here is the equal button, right? And so suppose I wanted 6 to the 3rd power. Well, 6. Now notice there's not an x to the 3rd button anywhere. We don't really have that, right? But we do have this button here that's right above the division button, and it's called a caret. So I push that button, and notice that it brings up a place where we put in an exponent. So 6 to the third, and hit enter. We see that's 216. Well, what if we did 6 to the, and remember over here it was the fifth power, 6 to the fifth, and hit enter. That same 7,776 that we got. All right. So just thought I'd pull up the calculator there and share that with you. If you just need to square something like 9 squared, you can use the square button over here, and we get 81. Notice if I do 9 caret, that up button, and still put in a 2, I'm going to get the same 81 either way. But if we need 9 to the 7th power, we do 9 caret button to the 7th power, and we end up with this big, what is that, 4,782,969. That would be a lot of math to do by hand. So good to know where those buttons are. All right. So that completes all of my instruction for Chapter 1, Lesson 2, titled Powers and Exponents. Remember, the base is the number that's being multiplied over and over. The exponent is how many times that we're going to multiply it. And if you have a base and you have an exponent, then you have a power. Thank you.